Questions on assignment 3. Okay. So last time I gave a problem that maybe you might give a try, and we'll go over that. Why don't we do that now? So another example. Prove that if A intersects B is the empty set, then A union B complement is equal to B complement. Okay, so it's an if-then statement. So there's, again, the three strategies. There is direct proof. Right, assume, so for P implies Q, right, assume P, show Q. There's the contrapositive proof, which is assume Q naught, show P naught. And there's the contradiction proof, which is assume P and Q naught, find R and R naught. Okay, so those are the three basic strategies. Here we'll just do a direct proof again. So to do a direct proof, we have to assume the hypothesis. So assume that A intersection B is equal to the empty set. Okay, and now we want to show that A union B complement is equal to, oh wait, was that the one? Was that the one we did? I think it was an intersection problem. Where is it? No, this is the one we did. Here's an example. Oh, for next time, prove this one. If A intersection B is the empty set, then A intersection B complement is A. Yeah, this is the example we did last time. And now this is another problem very similar to it. Okay, so we assume that A intersection B is the empty set. And now we want to show that A intersection B complement is equal to A. So there's two directions to do here. There is showing that A intersection B complement is a subset of A, and the other way around, that A is a subset of A intersection B complement. So what's the first sentence here? Let X be an element of A intersection B complement. Okay, now we need to show that X is an element of A. Well, what is A intersection B complement? Well, by definition, this is what? By definition, what? X is an element of
A minus B.
Right, but more directly, X is an element of what? And
No, element of A and an element of B complement.
X is an element of B complement. But we get that X is an element of A, right? So by definition, X is an element of A. So you don't even need to say this, or you can if you want. It's just sort of superfluous to say it. X is an element of A, and X is an element of B complement, and we're done. So it's more or less just by definition, right? You're trying to show that A intersection, right? I mean, anytime you have a set A and you take the intersection with some other set C, right? The intersection of A and C is right there, which is, of course, a subset of A. So just by definition, it comes out X is an element of A and X is an element of something else. But it doesn't matter. X is an element of A. All right. So now the other way around, this is the part that needs a little bit more thought. You want to show that A is a subset of A intersection B complement. So let X be an element of A. Now we want to show that X is an element of B complement as well. Well, what can we use now? What bit of information can we use now? We haven't used that assumption yet, that overall assumption of the hypothesis.
Yeah, the A intersection B is the empty set.
Right, because A intersection B is the empty set. Right, so here's A, here's B, and here's X. Because A intersection B is the empty set, where is X not? Right, X is in A, but A and B don't. So X is in A.
Not in B.
X not in B. I'm sorry, your voice is cutting out. Right, X is
not in B.
X is not in B. In other words, it's not a comma actually there, it's a semicolon. In other words, X is where? X is not in B. In other words, X
is in A intersection B, or X is in B complement.
X is in B complement, therefore.
Okay.
Yeah. Therefore, X is in A and X is in B complement. So it's,
yeah, we have to say that first.
Yeah, you don't have to. I wouldn't mark it wrong. And that's it. So no huge big deal there. This one. Right, so again, take a look at what we just did. So we're trying to show if P, then Q. So we assumed P, and then we showed Q. What's involved in showing Q, that two sets are equal? Well, you showed that A intersection B complement is a subset of A, and A is a subset of A intersection B complement, therefore the two sets are equal. So then the final part of the introduction to proofs that we started last time is talking about logical equivalences. Okay? With a logical equivalence, P if and only if Q, remember the double implication tautology. The double implication tautology is that P if and only if Q is logically equivalent to P implies Q and Q implies P. It's just like saying that two sets A and B two sets A are equal to B is logically equivalent to saying A is a subset of B and B is a subset of A. Very, very similar to that. Almost the exact same thing, really. Just sort of one is said in terms of sets, one is said purely in terms of propositional logic. Okay? So some very similar ideas going on here. So P if and only if Q is logically equivalent to P implies Q and Q implies P. So a proof that P if and only if Q is true could be one of two things. A chain of logical equivalences, right? So you assume P, right? And then you say, well, P is logically equivalent to A via some reason, which is logically equivalent to B via some reasoning, so on and so on and so forth, till you get to Q. So the chain of logical equivalences, like we've been doing. This is not the norm. It's not normally done this way because often you can't, except in very simple circumstances. We'll go over some things like that. Okay. But normally that's not the way it happens. And if it does happen that way, it's often because of this. So you prove both of these. A proof that P implies Q, along with a proof that Q implies P. And then maybe you'll notice that the proofs are the same forward. This proof going forward is the same as that proof going backward. In which case you could have done it this way. So you get that after the fact. Anyway, this is normally the way one goes about proving a if and only if type statement. Is proving the two implications, right? So with each one of these implications, you can do it direct proof, contrapositive, or contradiction, whatever suits the occasion. So one way I often like to do it is you prove that P implies Q, and then P naught implies Q naught. So this one is done by contrapositive. So that's one way I often like to do it. Although you don't have to. I just kind of like the way it feels. All right. So here's an example. Prove the following is true. A is a subset of B if and only if A union B is equal to B. All right, so here's the way the proof looks. So often you'll write a couple arrows. So this arrow is for this implication, and this arrow is for that implication. All right, so you're tipping off the reader as to where you're going here. So let's actually do it. Both by direct proof. So assume A is a subset of B. Now we want to show that A union B is equal to B. Right? So, how does one go about doing that? Well, you want to show that B is a subset of A union B, and A union B is a subset of B. Well, this one is more or less by definition, right? Let X be an element of B, therefore X is an element of A union B. Just by definition, it's the set of all X such that X is in A or X is in B. Period. Nothing more to say than that. And now the other way around, this takes a little bit more thinking. Not much, but a little bit. Let X be an element of A union B. Thus, X is an element of A, or X is an element of B. Right, so again, you've got the either-or situation. Either X is in A, or X is in B, or both. So you have to consider each case separately. Okay? So when there's two cases, there's one linguistic convention, one very annoying 19th century or even older linguistic convention that people should have abandoned a century ago, but still haven't. And that is what, when you're considering two cases. I'm sure you've seen it before. So, right, we have two possibilities, right? I mean, either it's sunny outside or it's raining outside. In the former possibility, we'll do this. In the latter possibility, we'll do that, right? In the latter possibility, we are done. Latter means the later one. So I'm sorry to subject you to this if you haven't already been subjected to it, but you know, you'll need to see it at some point in time. So in the latter case, we are done. Right, we wanted to show that x is an element of B. So when x is an element of B, we're done. So in the latter case. In the former case, so latter is the later one. In the former case, that's when x is in A. It's much clearer to say if x is in B, then we're done. It's much clearer to say that. I mean, not that you can't say the former and the latter, but you know, it's much clearer the other way around. In the former case, right? In other words, when x is in A. So let me erase the usage of former and latter and just say if x is in B, then we're done. If x is in B, then we're done. You know, familiar with that former and latter stuff? If you've taken any philosophy classes, you would have.
Yeah.
Yeah.
And writing papers.
Yeah, and Phil, more you know, prosaic type writing, you see it a lot. Although people do it in math, and I still find it annoying. If x is in A, then how are we going to get that x is in B? Oops, that's lowercase. Then because what? If x is in A, then because what? Then because A is a subset of B, we get what?
X is in B.
Yeah.
The implication.
X is in B. Right. And that's it, right? So we've got B subset of A union B by definition, more or less, and A union B is a subset of B. So therefore, they're equal. You know, one can conclude that B is equal to A union B at this point, period. One could say that, but it's superfluous. There's no need. Just end it there. If it, you know, I mean, there's sort of two purposes to writing out the proof. I mean, the main purpose is to communicate to your reader what you're trying to say, in which case you should be as brief as possible. And if the reader needs clarification, he will ask, or if the reader doesn't believe you, he or she will ask. But the other purpose is personal, like you write out the proof to teach yourself what's going on. In which case, you write out what you feel is necessary for you to understand what's going on. And then later on, when you revise your proof, you might make it more streamlined. Okay, so now we want to assume that. So first we assume that A is a subset of B, and we proved this is true. Now we want to assume that A union B. Well, let's do it by contrapositive. Or no. See, because it's not going to be as nice. Because when you say two sets are not equal, it means there's something in here that's not in here, or there's something in here that's not in here. So that's more complicated. We'll just do a direct proof. Okay, so assume that A union B is equal to B. Now we want to show that A is a subset of B. So we do what? I want to show that A is a subset of B. So we do
Assume A union B equals B.
right. So assume that. Next we do what? Let
X be an element of B.
A. We want to show A is a subset of B. So let X be an element of A, and now we will show that it's in B. You can maybe make that these two sentences one sentence, but that's fine. Let X be an element of A. So because X is an element of A, X is an element of what?
B.
Not quite yet. It's an element of
A union
A
B.
union B. Right? By definition. So therefore, by definition, let's be a little bit more particular. By definition of unions, X is an element of A union B, right? But then, since A union B equals B by assumption, right, we now have that X is an element of B, period. Right, so we assumed the hypothesis, so we're doing the implication this direction. We assumed this was true, and then we showed this was true. So assuming this is true, now to show this is true, you let X be an element of A, and you show that X is an element of B. Right? So just one subset containment. Right? Here we had two subset containments, but anyway. And that's the end of that proof. Okay, for next time, so that problem I gave you last time, that's not just an if-then, it's actually if and only if. So for next time, prove the following. Is true. So it's not just that if A intersection B is the empty set, then A intersection B complement is A. It's if and only if. So it's implication in both directions. Okay. By the way, just so you know it, I don't normally use it, but here it is. So by the way, when people write IFF is an abbreviation for if and only if. It's pretty standard, and people use it a lot. I try not to, but sometimes I sort of slip up and put it in there. But so IFF means if and only if. All right. One final topic here in set theory. given two sets A and B, right, the Cartesian product or cross product cross product is not used as much. Cartesian product is more the correct term. The Cartesian product or cross product is used for other things. Is so AXB, it's the set of all. These things are called ordered pairs, little a, little b, such that A is in A and B, little b is in B. All right, and this A and A comma B with round parentheses, not with square parentheses or curly brackets, is called an ordered pair. In other words, order matters. Right, so order matters. For example, like the pair 3, -4 is not equal to the pair -4, 3. Whereas, right, the set 3, -4 sets are not sets of size 2. Well, sets in general don't have order to them. Right, so there's no inherent ordering to the pairs, but with ordered pairs there is. So, for example, let's let A be equal to 1, 2, 3, and B be equal to the set 3, 4. All right, so A cross B is equal to, well, it's the pairs from A and B. All right, so we've got 1, 3, 2, 3, 3, 3, 2, 1, 3, wait, what did I do? Yeah, 1, 3, 2, 3, 3, 3, 2, wait. Then 1, 4, 2, 4, 3, 4. You could also do the Cartesian product B cross A, which is going to be different, right? It's all these pairs flipped. 3, 1, 3, 2, 3, 3, 4, 1, 4, 2, 4, 3. What's the intersection of the two sets? A cross B intersection B cross A is equal to what? What's the intersection of those two sets? Remember, order matters in pairs. So 1, 3 is not the same as 3, 1. But there is one pair that's in both of those sets.
3, 3.
Just the 3, 3. All right, so with ordered pairs, you write them using round parentheses, tipping off that the order matters. With with sets that you tip off using curly brackets or or braces, the ordering doesn't matter. But this is just a set with one thing in it. Okay, I mean, of course, oh, by the way, so you can also take products of cross products or Cartesian products of a set with itself, A cross A. That's going to be 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, comma, 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 comma. And B cross B is just going to be 3, 3, 3, 4, 4, 3, 4, 4. Right, and then, of course, in calculus, and pre-calculus, I mean, all the way since 6th grade or whatnot, is familiar with the XY plane, which is actually a geometric picture of the real numbers cross the real numbers, right? So ordered pairs of real numbers, right? That's just the XY plane. Or if you've taken Calc 3 already, the XYZ space. By the way, what's the order of A cross B? I mean, if A and B are both finite sets, if A and B are finite sets, right, then the order of A cross B, or the Cartesian product of A and B, is just equal to what? I mean, we've seen it in so many examples here, and of course we all know how to count how many chocolates there are in a box of chocolates, because it's just what? The number of rows times the number of columns. With the Cartesian product, that's just what? In terms of A and B.
Two times 3.
Right. The order of A, which is 3, times the order of B, which is 2. In those cases. But I mean, here, in general, it's just like that. Right, so this one's got order 9, this one's got order 4, and these two both have order 6. Right, this is order 3 and order 2, so that's order 6. This is order 3 and order 3, so that's order 9, order 2 and order 2, so that's order 4, so on and so forth. Now, of course, you can also do Cartesian products of 3 or more sets can also be defined. So if you have a bunch of sets, A1 cross A2 cross AN, it's the set of all, and these are called tuples, ordered n tuples, A1, comma A2, comma AN, such that little ai is an element of the set AI. Right, so like in Calculus 3, you work with R cross R cross R. Has anyone taken linear algebra yet, elementary linear algebra, or matrix theory? Right, I mean, in there, you work with R to the n, right, Euclidean n space, right, which is vectors of length n. And typically they write the vectors of length n as columns rather than as rows, but it's the same kind of thing, right? Typically they're thought of as rows, but you can do them as columns as well, A1, A2, up to AN, like that. And that's often thought of as Rn, which is R cross R cross R n times. Okay, so these are just formalizing notions that really you're already familiar with. So I have one question on assignment 3 where you're asked to do a Cartesian product right here. Okay, but we'll do examples of Cartesian. We'll do problems that work with Cartesian products throughout the semester. I don't know why, but it tends to be something that's confusing at first. Okay, so spend just a few minutes with it, thinking about it for this assignment, and then we'll talk more about it throughout the semester. But it's an important concept, and it's going to get used a lot when you go to algebra, modern algebra 4510, math 4510, and 4520. I think less so in real analysis. If you take linear algebra, it's used as well, or advanced linear algebra, or related algebraic type courses. All right. So one more topic here. I'm not going to test you on it, or give you a homework assignment or hold you responsible. It's more of an extra topic, but it's pretty neat. So,
Is it the continuum hypothesis?
yes, infinite cardinalities. Well, I'm not going to do the continuum hypothesis. Just going to talk about infinite cardinalities. So
It's fun.
the set of natural numbers. Right, so the set of natural numbers is an infinite set. So normally, I don't know, some people start with 0, other people don't. All right, the set of natural numbers has infinite order. Okay. Some folks leave out the 0. Use z plus, the positive integers, for n instead. But we'll just go with that. Z plus. So the cardinality has infinite order, or cardinality. But more specifically, z plus, or n, is called, well, let's use n. The order of n is called, well, different things. Countable, or countably infinite, or innumerable. So countable, countably infinite, or innumerable. Why? Because, well, those are the numbers we use to count. And we never stop counting. It keeps going and going and going, but we have, a notion of one coming before the other. Right? So 3 comes before 4, 4 comes before 10 million, 10 million comes before bazillion, whatever it might be. But every number has its proper place in a linear ordering, right? Now, two sets are said to have the same cardinality or order. When there is a 1-to-1 correspondence between their elements. Right, so two sets A and B are said to have the same order when there's a 1-to-1 correspondence between their elements. For finite sets, that's great, right? I mean, it matches up the way we like things to be, right? Here's a set of size 3. And here's a set of size 3, A, B, C. And, you've got a 1-to-1 correspondence between their elements. There's several of them. I mean, 1 corresponds to A, and B corresponds to 3, 2 corresponds to C. There's 3 factorial or 6 ways to make a correspondence, but there is a correspondence. So with finite sets, right, that matches up nicely with our notion of the order being the same. Right? There's a 1-to-1 correspondence between the elements. Right? I mean, how did people, start learning how to count way back when, before there was even a notion of numbers? People just used to use tally marks. Right? There was these tally sticks that people would find. They were sticks marked with little tally marks, and out in caves there'd be, tally marks on the wall. People just used to tally things up before they had a concept of numbers, much less arithmetic. So this is essentially that concept. But with infinite sets, things get more interesting. So here are some. So when a set A has a 1-to-1 correspondence with n, we call it countable. Right, so let's take A to be equal to the set of even integers. 0, 2, 4, 6, 8, 10. Right, the even natural numbers. So we'll just call it E. So on and so forth. Right, so at some point you get to 2n, so on and so forth, like that. So what's the correspondence? Well, this one will correspond to 0, this one will correspond to 1, this one will correspond to 2, this one to 3, this one to 4, this one to 5, this one to n. Right, that's the correspondence right there. So even though, so we say that A and N, E. That E and N have the same order, even though E is a proper subset of N, right? I mean, the even natural numbers is a proper subset of the full set of natural numbers, but there's a 1-to-1 correspondence between them, right? So that the elements match up in some way, not just in this way, but in other ways. So E is countable. Countably infinite. So that certainly doesn't happen in finite sets. I mean, if you got a finite set of order 20 and you take a proper subset of a finite set of order 20, is it going to have order 20? Right? I mean, if you have a set.
No.
No, of course not. Right? I mean,
Shouldn't.
if you got 20 things and someone takes 2 of your things, you got 18 things left. Right? So when you have a proper subset of a finite set, they don't have the same order. But with infinite sets, yeah, they can still have the same order. Right? So weird things happen with infinite sets. Right? Is that a proper subset can have the same order, and that's countable here. How about the set of all integers? Is that the same cardinality as n? So z, which is equal to the set of all integers, which is 0, -1, 1, -2, 2, -3, 3, -4, 4, is also countably infinite. Right? What would be the correspondence? Well, I mean, just from the way I've written it, you know, that's the correspondence right there. Right? I've listed them out in a linear order, right? And each number has its proper place, and you can determine what that proper place is, right? So this is -n, n, so on and so forth, like that. So here is the correspondence with n. All right, so that's 0. This goes with 1. This goes with 2. This goes with 3. This goes with 4, 5, 6, 7, 8. So n is going to go with which natural number? And minus n is going to go with which natural number? All right, look how it's going on here. This goes with 2. This goes with 4. 3 goes with 6. 4 goes with 8. So n is going with what?
N times 2.
Yeah, 2n. And -n is therefore going with
-2n.
Well, negative
Or 2n minus 1.
2n minus 1. There you go. All right. So again, even though the natural numbers is a subset of the integers properly, they still have the same order. N is a proper subset of z. They still have the same order. Countably infinite. Okay, so how about this? So let's just do z plus, just the positive integers. Z plus Cartesian product z plus. So this is still countably infinite. So the Cartesian product of two countably infinite sets is still countably infinite. So here the way you order things is not quite so obvious, but here it is. 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 3, 1, so on and so forth. They keep going like that. Right? Each row is countably infinite, but the Cartesian product of a countably infinite set is still, let me get my pen to work properly, is still countably infinite. Trying to line them up so it looks nicer when I show you the correspondence. Okay. So 3, 1, 3, 2, 3, 3, 3, 4, 3, 5. And this example is going to be even more important, as you'll see in a moment. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 4, 7. One more. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5. And then those rows keep going, of course, till we get down to like N1, right, and then N2, N3, and then it keeps going after that. Okay, here is the correspondence. So I'm just going to leave out the 0 this time because we'll just put the 0. Just leave out the 0 for this time. It's fine. And did I still didn't get it squared, did I? That's fine. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 13, 14, 15. And then 6 is down here. 6, 1, 15, 16, 17, 18, 19, 20, 21. You know, and it keeps going like that. Do you recognize these numbers up here? Do you recognize those numbers along the top row? You have encountered them, I guarantee you. Well, I don't know. In your generation, maybe not. My generation, yes, we've seen them. Because my generation, you know, not that we didn't have video games, we did. I mean, we certainly didn't have mobile phones, but we had video arcades that we had to go to. And in the video arcade that you went to, well, there was a standalone video arcade or it existed where? Those old video arcades, they existed along inside of what? No older folks in there? It's probably an activity you did when you were little, maybe. Unless you're really good at it, in which case you may have kept doing it. But for us, we had to do it because we had nothing else to do. We had to go. Had to go bowling. Right? And in the bowling alley, right, at the end of the alley, you have how many pins? How many pins in the rack? Oh, I'm sorry. It's time to go. We'll finish this one next time. There's just a couple more things, but this example has got more to it than than just this example itself. Okay, so so next time, please do that problem I gave you, and we will see you. Where is it? Please do this one for discussion next time. The one I gave you, where did it go? Here. All right, we'll start with that. Okay, have a good day, everybody.